Hello everyone, today I'm going to talk about normal distribution. So today's lecture will be divided into 4 parts. So the first part is to introduce normal density curve, and the second part is to talk about standard normal distribution and how to calculate z-score and probabilities. So the third part is an important property of normal distribution, which is called the empirical rule. And at last, I will talk about how to use normal distribution to approximate binomial distribution and proportions. Okay, so let's start. So the first question you may ask is, why do we care about normal distribution? So the answer to that is not that easy. There is a mathematics theorem called CLT, which is short for a central limit theorem. That theorem tells us that if we have a large enough samples, then the sample mean will follow normal distribution. So that's one reason why normal distribution is important. Another reason is that a lot of data in nature, they just follow normal distribution. Here is one example. So this data set called height data includes 25,000 records of human heights and weights of 18 years old children. You may take a look after the class, but I import this data set into our software and I plot the histogram and overlay with the density plot. You can take a look. Please, next slide. So you can see that the empirical density plot, which is in red color, sorry, is really close to the fitted normal distribution, which is in blue color. So in this example, we can say that normal distribution is good enough to describe this height data. And also this is an evidence to say that normal a lot of data just follow normal distribution. So what is a normal distribution? So a normal distribution has a lot of important properties. So the first one is the normal density is completely described by 2 parameters. So the first one is called the mean, which is always usually denoted as the Greek letter mu, and the second parameter is the standard deviation. So the mean determines the center of the distribution. It is located at the center of symmetry of the curve. In other words, it describes the location of the distribution. So if the mean of a normal distribution is small, then the density curve will shift to the left. And the second parameter, which is called standard deviation, that describes the spread of the data. The higher the standard deviation, the flatter the density curve is. So this slide is visual illustration of how parameters mu and sigma control the normal curve. So if you change mu, then you shift this density curve. You shift this density curve. Well, if you change sigma, if you increase sigma, the curve will be flatter like this. This is sigma, it's large. Okay, so if you have a small sigma, say, then the curve will be like this. This is small sigma. Okay. So to define normal distribution rigorously, we need the definition of probability density function. So as we know that in discrete case, we have a probability mass function. But in continuous variable, in the case of continuous random variable, we need to use the concept of probability density function to describe the distribution. So if we have a PDF or probability density function of a random variable that totally describe the distribution of the random variable. So how do we know from probability density function? How do we calculate probabilities using probability density function? It's easy. It's like you just integrate this. Suppose this curve, this like red line is the PDF of one random variable. Like so, if a random variable x follows the PDF, then if we want to calculate the probability of the random variable smaller than some specific value x naught, then we just integrate this area from negative infinity to x0. So in other words, the area under the curve like is the probability, is the corresponding probability. So what is the PDF of normal distribution? So it's like this. You don't need to remember this exactly, but you need to know the meaning of sigma and the meaning of mu. So this sigma is just the standard deviation, as we said before, and the mu is the mean of this normal distribution. So because it's a probability density function, the integral from negative infinity to positive infinity, that should be 1. That's probability density function has to satisfy. So in other words, so if you have a normal curve like this, so under the curve, the area should be 1. Okay, so this is normal. So for any PDF, the density curves must satisfy this equation. So normal density is just a specific case of PDF. So a normal distribution must satisfy this condition too. So because we have mu and sigma, 2 parameters, so we have a lot of normal distributions. But for different values of mean and standard deviation, we want to find like a standard form of normal distribution. So we don't need to like integrate like a lot of different normal distributions, because the normal density curve is hard to integrate actually, because it's e to the negative x squared over 2. There is no closed form for that integral actually. So people think of a way to like convert normal distribution to a so-called standard normal distribution. So how do we convert the normal distribution to standard normal distribution? You just use the formula. Like you use z equals to x minus mu divided by sigma. So suppose you have a big x like follows normal distribution with mean, mu, and sigma. Then you just calculate x minus mu divided by sigma, and that value called z will follow standard normal distribution. What is standard normal distribution? I would say, so standard normal distribution is with mean 0 and standard deviation 1. So mean equals 0 and sigma equals 1. That is standard normal. Okay. So somebody just calculate the integral of a standard normal distribution, so we don't need to integrate like a lot of other normal distributions. But this is an optional slide that tells you why, using the above formula, this z will follow a standard normal distribution. So any linear transformation of a normal random variable will also follow normal distribution. This is a theorem or the basic property of normal distribution. And also, you can use the property of expectation. So you can using the first property, we can say that z actually, because you calculate z by x minus mu divided by sigma. So this is a linear transformation of x. So z will also follows normal distribution, right? Okay. So because we know z follows normal distribution, to prove that z follows standard normal distribution, we also need to know what is the mean of z. So in other words, the expectation of z, and also the variance or the standard deviation of z, because variance of z is just the square, square of normal distribution. So it's just a square, sigma square. Okay, you can just have a subsquare of z. So we can use the properties of expectation. So when you calculate the expectation of z, so you just plug in how to calculate z. So you plug in here. So it's the expectation of x minus mu divided by sigma, and you can put sigma out, and then because mu is not a random variable, so mu is just a number. So you don't need to worry about the expectation of mu. It's just a mu, and you know that the expectation of x is mu, because mu is the mean of x and sigma is the standard deviation of x. So this one is 0. And also for the variance of z, we can calculate using some property of variance. So you can have that the variance of z is 1, which means the standard deviation of z is also 1. So z follows normal standard normal distribution. Okay, so suppose we have some z follow standard normal distribution. How do we calculate the corresponding probabilities? So you can use z-table or any software. So first I will tell you how to use z-table to calculate the probabilities. So suppose now you are interested in z equals to 1.151, right? So basically you want to find the area under the curve. So suppose z is 1.51 now. You want to find this area. How do you do that? You use this table. So first you find what are the two first digits. It's 1.5, right? So you look at this row. And then what is the second digit? It's 1, right? So you just look at this column. On this row, right? So what is the intersection? It's 0.9345. That's the area. That's exactly the area. That's how you do it using z-table. I will practice it after this slide, and we also have a lot of practice like using z-table in the homework actually. All right, this is just the same thing I talked about. So how do we calculate the probability using software? So I will talk about it, like how to use it in R. Just keep it. So how to do it? Like suppose you're interested in z equals to 1.51. Okay. So you just use this p norm 1.51. Then it will give you exactly the same thing, right? If you remember correct. If you remember what's the probability, it's 0.9345. In this case, it's 0.93447, and which is more accurate. Okay, so p norm calculates the probability corresponding to this 1.51, which is called z-score. Okay, you can also use q norm. This is a reverse operation. Okay, the reverse problem is like when you know the probability, you want to know the corresponding z-score. So you can draw it like this. Oops. So you can draw it like this. So suppose this is a normal curve, and as you can see, this is the mu, right? And you know, because we know the whole area under the curve is 1, so the probability cannot exceed 1. So suppose you are interested in probability that 0.9, you want to know which z-score is corresponding to this area, right? So you may want to know, so suppose this area is 0.9, and this is standard normal, they're normal, and you want to know the corresponding z-score. This is a reverse problem of the previous one, right? So this is easy. You can do it in Z table too. Like I will tell you after I tell you how to do it in R. So in R, you just, instead of using P norm here, you use Q norm. So because say you are interested in 0.9, you just put in 0.9. Because it's standard normal, you don't need to add any other like parameters. You just use this one. See? This is magic. So you get 1.28, which means this z-score is 1.28. To make sure you understand, let us look at the z-table again. As I said before, we are interested in probability 0.9, so we look into this table and find out which number equals to 0.9 or closest to 0.9. Let's look, see, and finally you'll find out this one. Which is 0.8997. So this number is closest to 0.9. So we just find out the corresponding z value. We look into the row, which is, so this tells me the first two digits, the first two numbers of z is 1.5. And what is the second digit? It's 8, right? So it tells me that this corresponding z-score is 1.28, which is the same as the result of in our software, right? So let's continue. Okay, so we illustrate how to do Q norm and P norm in R. So let's do more practice. So suppose a random variable z follows standard normal distribution. Find out the following probabilities. You may want to pause the video for some minutes and find out yourself. I'll do it like afterwards. Yeah. Okay. Hopefully you find that you figured out the answer. So what's the probability that z smaller than 1.5? Let's do it in z table first. This is our familiar z table. You just use this row, right? 1.5, and the second digit is 0, so it's 0.9332. Okay, so this is 0.9332. Okay, so what is the probability that z smaller or equal to 1.5? What's the probability that z equals to 1.5? It's 0, because z is a continuous random variable. For a continuous random variable, the probability that a continuous random variable equals to a specific value is 1. It's 0, sorry. It's 0. Because no matter like which density you have, what's the area of this line? So I need to erase this. Okay, so what is the area of this specific line? This specific line is just 0. because it doesn't have any length. It only has this y's, or you only have this length, you don't have y's, so it's 0. So what is the probability that z is smaller or equal to 1.5? It's still this number. That. And then what is the probability that z is bigger than negative 1.5? So suppose this is 1.5, negative 1.5 is here. What is the probability that z is larger than negative 1.5? Do you remember the important property of normal distribution? It's symmetric. Yeah, it's symmetric with respect to the mean. So the mean is 0. So these two are symmetric, right? So what is the probability that z is larger than negative 1.5? It's the same of this area, the vertical line area. It's the same as the probability that z is smaller than 1.5. So what is the probability that z is between negative 1.5 and positive 1.5? Think about it. You can use z-table, or you don't need to like look up into z-table, and you can solve this problem using this number. How do you use this number? Like first, you can I'll erase this because it's a mess. It's a messy. Okay, so how do you do that? So you have this normal density is 1.5. This is negative 1.5. They're symmetric according to this 0, which is the mean of the standard deviation, standard normal distribution. What is the probability that z is in this area? So we know that what the probability that z is smaller or equal to 1.5 is 0.933, right? And you know a fact that under the standard normal density, the whole area on the real line is 1. So you use 1 minus 0.933, and you got this area. And since it's symmetric, you know this area equals to this area, and you use 1 minus these two areas, and you got the area in the middle. So you want to write down like a explicit mathematical expression. You do 1 minus 2 shaded area. So what's the shaded area is 1 minus probability z smaller than 1.5. Right? So what's this? It's 1 minus 2 times 1 minus 0. And you can calculate by heart. So it's just 0.067, and multiplied by 2 is 0.1134. You use 1 minus that is 0.866. Okay, so you got it. And then let's look at another like actual example. So this is an exercise. Like suppose the weight of an navel oranges is normally distributed with mu equals to 8 ounces and standard deviation sigma equals to 1.5 ounces. Answer the following questions. So what's the proportion of oranges that weigh more than 11.5 ounces? Or you can phrase it as, if you randomly select a navel orange, what is the probability that it weighs more than 11.5 ounces? You may want to pause the video and solve for yourself. Okay, hopefully you got the answer. So how do we calculate this? Like this is not standard normal. It's like a general normal distribution with mu 8 and sigma 1.5. So first, if you see this question, you want to convert a general normal distribution to standard normal distribution. How do we convert that? Use z-score, this formula. Sorry. Right? So because you are interested in 11.5, you just use 11.5 minus mu, which is 8 divided by 1.5, right? So it's just 3.5 divided by 1.5. This is the z-score. And you use calculator to calculate it. And then using this z-score, you can just use the table, right? You want to find what proportion of oranges weigh more than 11.5. So if you use z-table, suppose this is called z-score, specific z-score. You use the table, you find this area, right? But you want to find the probability that the orange is way more than this z-score. You need to use 1 minus this area to get this area, right? Okay, so the answer is 0.0099. You can calculate, right? So there are two follow-up questions. So what proportions of oranges weigh between 10.3 and 14 ounces? And the last question is find the 80th percentile of the distribution. You may want to pause the video and do it yourself. Okay, hopefully you got the answer. So I will just briefly talk about how to do B and I will describe C in detail, and I will use R to solve it actually. So what proportion of oranges weigh between 10.3 and 14 ounces? You remember mu equals to 8, sigma equal to 1.5, so you just convert the normal distribution to standard normal distribution. So if we rephrase it in like a mathematical expression, you want to calculate the probability that suppose x follows the normal distribution of 8 and 1.5, so the probability is 10.3, right? So you first convert this one to z-score, and this one another z-score. So for 10.3, you calculate 10.3 minus mu, which is 8, divided by sigma 1.5. This is this z-score, and this z-score is 14 divided by minus 8 divided by, what is this? 14 minus 8 divided by 1.5. This is the z-score of 14. And then when you have this 2 z-score, you just look at the table and find out the probability or the proportion. So for C, you want to find the 80th percentile of the distribution. So in other words, you know the probability equals to 0.8. So you want to find the corresponding x, right? So this is a normal distribution. So you know this area is 0.8. So this is standard normal. So you find the z-score here. You can use it table or R. And then you convert it back to this specific general normal distribution because it's z equals to x minus mu divided by sigma. So how do we, if we know z, how do we know x? You just, x is equal, you multiply sigma on both sides and plus mu. So it's mu plus z times sigma, right? That's the answer. So I will do it in R. So we are interested in 80th percentile, and mu equals to 8, right? Sigma is 1.5. Oops, sorry. Sigma is 1.5, and we are interested in 0.8. So let's call it P equals to 0.8. Do you remember how to calculate back z-score when you know probability? You use Q norm, right? Q norm 0.8, and that will return your corresponding z-score. Okay, I will call it Z. So how do we calculate back the corresponding x value? Do you remember that formula I just derived? It's z plus mu, mu plus z sigma, right? So you just calculate mu plus z times sigma. that's the threshold you want to know. That's the answer. So we got all the answers to this exercise. Okay, so I will give you a chance to derive the empirical rule yourself. So the question is, how many percentages of data falls within 1, 2, 3 standard deviations from the mean? That's basically the content of empirical rule. I think you can do it because you know how to calculate z-score and how to get to know the probability. So you may want to pause the video for a while and think about it. Hopefully you can get the answer. So this is the visualized empirical rule. So what's the area? What's the area? Yeah. What is the area of this part? And what's the area of this part? And what's the area of this whole part? Please think about it yourself. Okay, hopefully you got it. So if a specific, suppose you have an x equals to mu plus 3 sigma, and this x follows a normal distribution with mean mu and sigma square, then how do you calculate the corresponding z-score? You just use x minus mu divided by sigma, right? So you plug it in, you get 3. So the corresponding z-score is 3, and for this one it's 2, and for this one it's just 1. So how do you calculate the probability or the area? You just use the table. After you look up the table, you will know the answer. So this is called empirical rule. So the beauty of normal distribution is no matter which and what mu and mu sigma are, the area between mu minus sigma and mu plus sigma is about 68%. The area between mu minus 2 sigma and mu plus 2 sigma is about 95%. The area between mu minus 2 3 sigma and mu plus 3 sigma is about 99.37%. So almost all values fall within 3 standard deviations. Okay, when you want, so this graph tells you the empirical rule, which is also called like 68, 95, and 99.7 rule. Okay, you got it. So the last part of this lecture is to use tell you how to use normal approximation to binomial. We learned binomial distribution before the class, so hopefully you all remember what binomial distribution is. So suppose you have a binomial distribution where n, which is the sample size, is large, and p, the probability of success in each trial. So if n and p is middle of the road, like it's not too large or too small, then you can use normal distribution to approximate it. So why do we use normal approximation? Because binomial distribution is kind of hard to calculate. Like we use a problem or practice problem to help you understand why do we use the approximation. So suppose you are performing a cohort study. If the probability of developing disease in the exposed group is 0.25 for the study duration, if you sample randomly 500 exposed people, what is the probability that at most 120 people develop the disease? Okay, so suppose you want to use binomial distribution to solve the problem. What is n here? N is 500, right? What is p? The probability of success in each trial. So it's 0.25, right? So that's the probability of developing disease. So this random variable, the number of people develop the disease, will follow binomial distribution with n 500 and p 0.25. And we want to know the probability that this random variable is at most 120, which means that x is smaller than 120. How do we calculate them? We add them up. So what's the probability that this x is 0? Add probability x equals to 1 until probability x equals to 100. And so you get the exact probability using binomial distribution. This is hard, right? So how do we do that? You plug in the the formula of binomial distribution. So as I said before, so this is how we calculate the probability of this one, right? So this one is this one, if you remember the formula of binomial distribution. So we have like 121 terms here. We need to add them up, and you can use some software to do it, like the final answer is 0.32. But if you use binomial distribution, this is easier to calculate. So we want to know that what's the probability that x is smaller than 120. How do we do that? You just convert to standard normal, use x minus mu divided by sigma. If once you have this, you just use the z-table. So what is mu here? What is the mean of binomial distribution? N times p. What is sigma here? The standard deviation of binomial distribution, square root np 1 minus p. So you just plug in, it's 500p, 0.25, plugging into this formula. This is the mean. This is the standard deviation. Then plug them in here and use the table to find the probability. This is much easier than this way. And you can see, if you calculate yourself, so this is the z-score, the probability 0.30. It's really close to the exact answer. So we can use normal distribution to approximate binomial distribution. That is much easier. So what about the proportions? So we know that proportion is just binomial distribution forms the basis of for proportions. A proportion is just a binomial count divided by the sample size n. So for example, if we sample 200 cases and find 60 smokers, so the observed proportion is just 60 divided by 200, which is 0.3. Okay. So because we can use normal distribution to approximate binomial distribution, we can also use normal distributions to approximate proportions. So it's just a change of n. So you can, if you are lazy, you just remember this formula. If you are not, you can derive it yourself. You just, yeah, I don't want to mention it here. You can do it after class. Okay, so binomial, the mean is n times p. The standard deviation is square root of n times p times 1 minus p. For proportions, the mean is p. The standard deviation is square root of p times 1 minus p divided by n. Just so p hat means the sample proportion, and you just remember that for binomial proportion, they differ by a factor of n, also for standard deviation. So next class, I will talk about I will have some exercise for you to calculate the probability of proportions, and to some, sorry, yeah. So it all comes back to standard normal distribution. So if you have n times p is like large enough, and like usually less than 5, then you can use, it's reasonable to use normal distribution to approximate. So to summarize, after the class, you should be able to describe normal distributions in your own words. And second, you should be able to calculate z-scores and probabilities under normal distributions. And third thing, you need to explain the empirical rule. And the last one is, maybe you, without exercise, like you can describe in your own words how to approximate binomial distributions and proportions using normal distributions. Okay, that's all. Thank you.